Okay, now we're looking at 5.8, and this is modeling with logarithmic functions. Remember, when we're modeling, what we're doing is we're using algebraic and we're using mathematical expressions to model real life situations. That's what we're doing. So some quick notes. Logarithmic functions can be used to model situations where inputs grow multiplicatively and outputs grow additively. We talked about that way back in like 5.4, where for logarithms, your input, the value you put inside, are going to grow multiplicatively, but your output, your powers, are going to grow additively. We can construct a logarithmic model from one x-intercept and a proportion, two input-output pairs, a verbal description of a scenario where they give us some of that stuff, or identifying transformations from parent functions. So if we know what the parent function is and we know how the transformations are happening, we can move the thing around and figure out what the equation should be. All right, logarithmic models are often used to determine the independent variable of an exponential relationship. So remember, that's going backwards on the exponential, and we're finding what the independent variable, the variable that you put in, is. It's essentially what that means is logarithmic models are used to find the powers of exponential relationships. All right, so let's look at number one. Dextromethorphan. Sure, we'll go with that. The chemical in Dayquil has a half-life of 3 hours. Suppose you take a single dose of Dayquil, which has 20 milligrams of that thing, the D word. Write a function for g of h that gives the number of milligrams remaining after h hours. All right, so putting everything together here, we've got g of h, and we're going to start off with 20, so that's your a1, and then it's going to decrease by half, so we're going to multiply by 1/2. How often are we going to multiply by half? Well, if h is hours, we're going to do that every 3 hours, so we're going to multiply by 1/2 h divided by 3. So once we get to 3, we're now going to have a value of 1 for that exponent, and 20 is going to be multiplied by a whole 1/2 to the first power. After 6, then 1/2 is going to be squared. You'll have 1/4 times 20, and so forth and so forth. So remember, whatever the period of the half-life is going to go in the bottom as long as the top is measuring time in whatever unit that is. If the units are different, you got to get the units to be the same. Otherwise, this doesn't work. All right, so there's your function. And after how many hours will there be only 5 milligrams of dex, that word, remaining in the system? In your system, explain your reasoning. So we're looking for where this thing equals 5. 20, 1/2, h over 3. So we want to find out and solve for h. So we're going to move the 20 over, divide by 20. So 5 divided by 20 is going to give you 1/4, and that equals 1/2 to the h over 3. Now, guys, here is where we can use that whole 1-to-1 thing. Is there a power we can raise 1/2 to get 1/4? Well, yeah, we can square it. If we square the top and square the bottom, we're going to have 1/4. These two are equal. And if these two are equal and we have the same base, that means that h over 3 must equal 2. So then we multiply both sides by 3, and h equals 6. So after how many hours will there be only 5 milligrams of dextromethorphan remaining in your system? 6 hours. So there will be 5 milligrams in my system after 6 hours. Do not leave it like that. Answer the question. And explain your reasoning. There's your explanation right there. If you actually worked it out mathematically, that is your explanation. You don't have to explain anything. All right, same question, part C and D. After how many hours will there be 16 milligrams of that thing remaining in your system? Explain your reasoning. So same thing. So you're still just going to solve it again. So 16 equals 20 times 1/2 to the h over 3. Divide both sides by 20. You get 16 over 20 is equal to 1/2 raised to the h over 3 power. 16 over 20, that's going to reduce to 4/5. So now we run into a problem where there's not an easy way to actually solve that for with the 1-to-1 property, because there's no power you can raise 4/5 to make it 1/2. Or sorry, there's no power you can raise 1/2 to make it 4/5. So this is where we're going to have to actually take the log. So we're going over here, and we've got, once again, 4/5 is equal to 1/2 to the h over 3. You'll see why I left that space here in just a second. Because now we're going to take the log, not natural log, base 1/2. And we're going to take the log base 1/2. Now why did we use 1/2? Well, we used 1/2 because our base of 1/2 is over here. We use the 1/2 because we want this thing to go away so we can get that h over 3 down on the base level, not as an exponent. So now we've got log base 1/2 of 4/5 is equal to log of 1/2 to the 1/2 h over 3. That's all going to cancel out. This part's going to, and it leaves us with just h over 3. So then we can continue solving this. Remember, all you want to do is solve for h. So we're going to multiply both sides by 3. So h is going to equal 3 times log base 1/2 of 4/5. Now, if it's not a calculator problem, that's as far as you can go. If it is a calculator problem, here's the thing. I don't know that I would necessarily go any further than that anyway. Now, we can find that exact value, and what we end up doing is we end up taking the log base 1/2 of 4/5, and that can be confusing sometimes in the calculator. Some calculators will not do this. You can do something called the change of base formula. I'll explain about it at some point. I guess I should talk about it anyway. I'm surprised we haven't already. But if you do that with a calculator, you're going to get just the log part is going to give you 0.32193. Multiply it by 3, and you get that h is equal to 0.9658 hours, or let's just say 966 hours. So in less than an hour, you're going to have your dextromethorphan or whatever down to 16 milligrams. So if you wrote all that out, after 0.966 hours, the amount of DEX in my system will be 16 milligrams. All right, and in part D, write a function for h of g that gives the number of hours until g milligrams of the initial dose remain in your system. All right, so back up here, remember h of t was what we had, and that's where we got the 20 times 1/2 to the h over 3. And that way we're plugging in time, and we're getting out the dose. Well, not the dosage, but the amount, the milligrams. So we're getting the milligrams out and plugging the time in. Sorry, that was G of H, not G of H. So the time is what was in the function, and the milligrams is what we get out. So now they want us to write one that's going to give us the milligrams, and we're going to put the milligrams in, and we're going to find out how much time it takes. So h of g is going to be the inverse of g of h. So let's say grams is equal to 20 to the 1/2, sorry, 20 times 1/2 to the h over 3. And then all we're going to do is we're going to solve for h. So we're going to solve for h to get it out. And first things first, we're going to divide by 20. Those will cancel out. So we end up with, let's scroll down here a little bit to get a little extra room. So g over 20 is equal to 1/2 h over 3. Now what do we need to do? Well, same thing we did up here. We're going to take the log base 1/2. So then once we do that, these are going to cancel out, leaving me with just h over 3 on the right. And over here, I've got log base 1/2 of g, not 9, g over 20. And then to get rid of the 3, I'm just going to multiply both sides by 3. So h is going to equal 3 times the log base 1/2 of g over 20. So there is your h of g. So all we did was find the inverse. We're going from one to the other at the first 3 parts of the problem. Then the last one they say find an equation that takes us the other direction. And that's all we did. All right, number 2. Number 2 says a logarithmic function f has an x-intercept at x equals 4. Okay, x-intercept at x equals 4. That means we have the point 40. And passes through the point 11, 6. So there's 2 points. If the equation for f can be written as f of x equals a log base 2 of x minus h for some constants a and h, find the values of a and h. All right, I'm going to rewrite the f of x as y, just so it becomes a little more obvious here. Y equals a log base 2 of x minus h. All right, so the easiest one to plug in is going to be this one to get some numbers quick. So we've got 0 goes in for the y. A is a log base 2 of 2 minus h. Sorry, 4 minus h. All right, so what do we know? Well, we know that if we take a log and the only way that that log is going to be equal to 0 is if this is 1. Sorry, had a brain fart there. That's not right. Erase all this. Okay, we're multiplying this. Let's think about it this way. We're multiplying this, and the only way that a times the log base 2 of 4 minus h is equal to 0 is if a equals 0 or log base 2 of 4 minus h equals 0. So we're going to assume that a is not 0. Typically because, well, if a is 0, then there is no expression. It's just always going to be 0. So let's not think of a as 0. But what about log base 2 of 4 minus h? If it equals 0, then this thing's going to be equal to 0 the same way. But what's the only way that this is going to be equal to 0? Well, the only way that that's going to be equal to 0 is, remember, your powers. 2 to what power is going to give you this number right here? Well, if we have 2 to the 0 power, we know this has to be 1. The 4 minus h must be 1. That's the only way that this thing works. So if 4 minus h equals 1, we can subtract 3. Why am I subtracting 3? Subtract 4, subtract 4. We're going to get negative h equals negative 3. And then that means that h equals 3. All right, so now we have one of the values, h equals 3. And then we can use the other point here to find out what a is. So if we plug, once again, we've got y equals a times the log base 2. I'm just writing this equation again, except for I know what h is now. I can plug that in, x minus 3. So now I'm going to take this point. Let me go ahead and change colors here. So I'm going to take this point. I'm going to plug those x and y values in there. So 11 is equal to a times the log base 2. Got that wrong. 6 is equal to a times log base 2 of 11 minus 3. Plug the x in where the x goes and the y in where the y goes. Don't do it like I was trying to. All right, so then we can start simplifying, and 11 minus 3 is going to be 8. So 6 equals a times the log base 2 of 8. And the log base 2 of 8, this thing right here, we know to be 3. So 6 equals a times 3, and we can just divide both sides by 3, and a equals 2. So then we can write all of our stuff back together, put everything back in, and what are we going to get? We're going to get that f of x, right as a function notation since that's the way they did, equals 2 log base 2 of x minus 3. So there's your equation right there. Just a little plug and chug 2 different times. Guys, when you're doing the first one, you've got multiple things that are unknown. You're going to look for one of those main properties of logs. That's why I chose this one first. If you plug this one in first and you don't have the 3, then you don't have enough information to solve it. Here, we've got this special property where the only way that this is going to be equal to 0 is if this is equal to 0, which means the only way that the log is equal to 0 is if what's inside the log is equal to 1. That's how we can break that down. Take the a out of the equation for now, because we know a is not equal to, not the thing multiplying that makes this thing 0. So we have to count on the log expression being 0. Then we can solve for what's in the log. Then we can come back, plug the other equation in, and solve for the a that's on the outside of the log expression. So use those log properties, those special things we know about logs, to be able to break them down first and exclude the things that are outside of it. All right, hope that helped a little bit.